We saw in the last lecture how to apply transformations such as inversion of source and load or a cascade connection of converters to take a DC-DC converter and generate a new DC-DC converter that has different, possibly desirable properties. The approaches that were considered in that lecture will not generate an inverter. So suppose we have DC-DC converters, but we want to make a DC to AC or AC to DC type converter. We need to be able to change the polarity of the voltage, and so far in the previous lecture none of those approaches would accomplish that. So in this lecture we'll talk briefly about one of the widely used ways to produce AC. And it's called the differential connection of the load. So if we have two DC-DC converters, what we can do is connect the load differentially between their outputs. So for example, suppose these converters are buck converters. Okay, so the first buck produces an output voltage that is the duty cycle times Vg, and it's a DC voltage. The second buck produces an output voltage that is its duty cycle times the input voltage, which is also DC. But we connect the load differentially between the outputs so that the voltage across the load is voltage 1 minus voltage 2. Now if both buck converters produce the same output voltage, then we will get 0 volts differentially across the load. But if we make one of the converters produce a higher voltage than the other, then we can get either positive or negative voltage across the load depending on which buck converter makes the higher voltage. And in fact, if we control the duty cycles of the two buck converters in a skillful way, then we could make, for example, a sinusoidal voltage that appears differentially across the load. So here we'll draw out the circuit. Here's buck converter number 1 with its switch and LC filter. Here's buck converter number 2 with its switch and LC filter. And what we're going to do is drive buck converter number 2 with the complement of the duty cycle of converter 1. So if we drive the transistor of buck converter 1 with, say, the duty cycle D, then buck converter 2 will have its transistor driven with D prime. Okay, so then the voltage across the load will be V1 minus V2, or dVg minus D prime Vg, and we can combine the D and D prime together to get this. 2D minus 1 is actually D minus D prime, or D minus the quantity 1 minus D. So we get 2D minus 1. Okay. Here's a plot of that conversion ratio, 2D minus 1 versus D. At D of a half, the conversion ratio is 0, and when D is greater than a half, we get a positive voltage, and when D is less than a half, we get a negative voltage. Now, this circuit can be considerably simplified. We have a lot of LC filters, and we can, again, like in the last lecture, simplify this filtering. And the first thing we might want to do is, if you look at this, you see we have capacitors that are connected from the individual outputs to ground, where what we might really want to do instead is directly put a capacitor across our load and filter the load voltage. So here what I've done is remove these two capacitors and replace them with a single capacitor across the load. Once we do that, you can see that now effectively we have our two inductors in series. So we could take those two inductors and combine them into a single inductor like this, whose value would be the sum of the two individual inductor values. And now you can see we have simply an LC low-pass filter that's taking the differential voltage coming out of the two switch networks and putting that through a two-pole low-pass filter to provide the load voltage. Okay, this is the way we most often build this circuit, and on the right side here is this exactly same circuit. It's just redrawn in the way it's normally drawn, where we have our two switch networks and the load and LC low-pass filters connected differentially across the outputs. This is often called the H-bridge or full bridge circuit or a bridge inverter circuit. It's very commonly used in single-phase inverter applications where we have a DC input VG and we want to produce a sinusoidal output across the load, V. It's also used in DC applications, for example in DC motor drives or servo amplifiers in control systems, where we want to drive a DC motor in either direction. So to drive the motor in one direction, we apply a positive voltage that's DC. To drive it in the opposite direction, we apply a negative DC voltage. And so we can do that with a circuit like this as well. We might, in that case, actually replace the whole RLC network simply with a DC motor connected differentially between these terminals. The self-inductance of the motor winding takes the place of this inductor, and the inertia of the shaft replaces the capacitor. If we want to make three-phase AC, we can do the same trick with three converters. So here we might have three different buck converters, one for each phase. Each buck converter produces an output voltage that is its duty cycle times the DC input voltage VG. And we connect our three-phase load differentially across the outputs of the three converters. Okay, so the line-to-line voltage from phase A to phase B will be V1 minus V2. The line-to-line voltage from phase B to phase C will be V2 minus V3, and so on, like this. So what we do then is we control the duty cycles of the three converters to make the three individual AC output voltages be the desired sinusoids with no offset or no DC bias. So here is that circuit. Here again we have three buck converters with their individual filters. As before, we can change the filtering, and again, instead of filtering the voltage from one phase to ground, we might instead want to filter the AC voltage. So we can move these capacitors across the AC load. Here the circuit is drawn with the capacitors omitted altogether, and we simply have the three inductors of the three buck converters and the three switch networks, one for each phase. If desired, we can put three-phase capacitor filters as well. For example, we could connect them in what's called a delta connection and make them filter each line-to-line voltage. Or in some applications, we might omit those capacitors. If we want to build a motor drive, we might replace this whole network with, say, a three-phase induction motor. The inductors become the inductances of the windings, and there will be also filtering from the inertia of the load. But effectively, we have a three-phase AC load that is connected differentially across the outputs of three buck converters. Here's another similar kind of circuit that has a boost type characteristic. There's a single inductor on the input, there are switches for each of the three phases, and we have capacitive filters on the output. And this is the current source inverter. It has a boost type conversion characteristic, but it has a similar three-phase bridge in it. In each of these circuits, I've drawn ideal switches, but of course we have to realize the switches carefully according to the procedures we discussed in Chapter 4. So for this circuit with the buck converters, our buck switches need to be current bidirectional switches because they conduct the AC output currents. And in the current source inverter, we need voltage bidirectional switches because they block the output voltages. But we've now already discussed how to do this, and we know how. Okay, so we've seen that the differential connections of DC-DC converters can lead to inverter-type characteristics and give us a way to really synthesize and understand where some of these inverter circuits come from. Now there are other ways to do it as well, but this differential connection is in fact the most widely used approach.